Hi, it's me, Alan. Today, let me tell you a story about black holes. What is a black hole? If you jump up, you cannot escape the Earth because you don't jump fast enough. You fall back down. If you take a plane, you cannot escape the Earth because even planes eventually have to come back down. They are also not fast enough. You fall back down. In order to escape the Earth, you need a rocket, because only rockets are fast enough. The force of gravity gets weaker as you fly further away from the Earth in a rocket ship. So you can get so far away from the Earth that you just keep going. The force of gravity is not strong enough to pull you back. You don't fall back down. You escape. The speed you need to escape the Earth is called the escape velocity of the Earth. If the Earth were heavier, you can imagine that you would need to go even faster to escape. The more powerful gravity is around something, the faster you need to go in order to escape. So the escape velocity depends on how massive an object is and how close it is to you. Let's talk about the speed of light, because nothing can go faster than the speed of light. We know this to be true. So what if the escape velocity is larger than the speed of light? Then you can never be fast enough to escape. If you're close enough to something heavy enough, the gravity might be so strong and the escape velocity might be so large that it is larger than the speed of light. In that case, even light cannot escape. For something very dense, imagine drawing a sphere around the object. Every point on a sphere is the same distance away from the center of the object. And that special distance is called the Schwarzschild radius. It tells you how close you have to be to the object so that gravity is strong enough, so that escape velocity is large enough that in order to escape you have to be going at the speed of light. This sphere is called the event horizon because nothing can escape from the inside. Events on the inside are isolated from events on the outside. Since light cannot escape, it traps light. It's black. There's no color because no light can come from this object, and so we call it a black hole. But you might ask, how can gravity attract light? We know that gravity is a force that pulls masses together, but light doesn't have a mass. Photons are massless. They don't weigh anything. So how can gravity pull on light if light has no mass? This, I believe, is one of the questions that puzzled Einstein and led him to discover the theory of general relativity. So let me roughly describe what general relativity says. The idea of general relativity is that gravity is general relativity. Mass sits in space-time. Space-time is 3 dimensions of space and time. Space-time is how we measure the universe and pinpoint where things are happening, both in location and in time. Mass sits in space-time and curves the space-time around it. And everything follows the bends and curves that space-time exhibits. Things try to move in straight lines, but the definition of a straight line is bent. Like going north on the Earth, if you go north from the equator, and if you keep following north, eventually you turn as you reach the poles. So even though you are walking straight north on the Earth, and from your perspective you're going straight the whole time, in reality you are curving because the surface of the Earth is curved. In a similar way, objects follow the bends and curves of space-time, thinking that they're going straight, when actually they are curving. So light following the curves of space-time also bends and acts as though it is being bent by nearby masses. It acts as though masses are attracting the light. When there's enough mass in a small enough space, space-time is curved so much that light cannot escape. We usually don't notice bending light on Earth. Space-time is not curved very much by the Earth or the Sun. They're not very massive or compact. So the space-time is nearly flat. So that's why we see light just moving in straight lines. But around black holes, it's so distorted. The space-time is curved so much that actually the distortion switches the meaning of space and time. The direction of the future, instead of being in time, the direction of the future starts to point towards the center of the black hole. So in order to move forwards towards the future, as we all do inexorably, we have to move towards the center of the black hole. Everything within the event horizon moves towards the center, because within the event horizon, time and space have switched meaning. This is what it means for mass to distort space-time. Because of the way mass bends space-time, time is mixed with space, and space is mixed with time. This extreme example helps us to understand why we fall towards the Earth. From a general relativity point of view, the Earth distorts space-time around it just a little bit, so that time is traded a little bit with space. So as we move towards the future, we too feel that in order to move in a straight line, and in order to move towards the future, we inevitably move towards the Earth. We fall towards the Earth, not using gravity as a force, but using gravity as this switching between space and time. To summarize, all massive objects have an escape velocity, depending on how close you are to the object and how massive it is. Close enough around a massive enough object, the escape velocity can exceed the speed of light, which nothing can move faster than. Then, because space-time is curved by massive objects, and all things, including light, follow those curves, nothing can escape a black hole. How do you make a black hole? To make Earth into a black hole, you would need to squeeze it into a 9mm space. That's the only way to make Earth's distortions of space-time significant enough so that it can trap light. To make the sun into a black hole, you would need to cram it into a space of 3 kilometers, about the size of a city. Let's put our trust in gravity to make black holes for us. Stars hold themselves up by nuclear fusion. They have a source of energy in their centers, and as the energy moves outward, it holds up the star against the inward gravity. But when stars run out of fuel, they run out of energy to support themselves. They start to collapse. As they collapse, they get denser and denser. The same amount of mass fits in a smaller volume, so they get denser and denser. They get so dense that electrons get squished together, and they provide pressure. But a star can be so massive that the pressure of electrons being squeezed forces electrons into protons. Positive charged protons plus negative charged electrons, the charges cancel out. You make neutrons. So when a star is massive enough, as it collapses, its protons and electrons become neutrons. Neutrons can provide even more pressure when they're squished together, but at a cost. Pressure is linked to energy, and E equals mc squared. Energy is related to mass. So therefore, energy and mass and pressure all bend space-time. The conclusion is that pressure makes the star's gravity even stronger. There's a tipping point where you add more pressure to support the star, but this makes the star even harder to support because the pressure adds to the gravity. So you add even more pressure, and the star's gravity gets even stronger. There can never be enough pressure to support the star. An analogy is the government. When the government borrows money to pay off its debts, it makes the debt even larger. If it can pay off the debts faster than it accrues interest, then the debt will shrink. But there's a tipping point because the government only makes so much money with taxes. So there's a tipping point where the debt just gets larger and larger because paying off the debt requires us to borrow money to pay off the debt every year. And so every year we borrow more money to pay off a larger and larger debt. Anyway, at the tipping point, no amount of pressure can support the star, so it keeps collapsing. As gravity brings it all together, the star gets denser and denser, smaller and smaller, until the escape velocity at the surface exceeds the speed of light. A black hole is born. Thank you very much.